Thank you. December 2018. David Kalschmidt from Grafana Labs was on the stage of KubeCon North America to introduce Grafana Loki, an open source solution to collect and query logs at scale. Now, fast forwarding a year and a half later, today Loki is generally available and is used by many companies and users as a logging solution. To give you an example, at Grafana, we have a Loki cluster for our own internal applications. We currently collect about 22-25 megabytes of log per second for a total of 2 terabytes of log per day. Last week, my colleague Cyril was tweeting about some performance improvements we are introducing in Loki. And in our internal cluster, this one, we are currently seeing about 10 gigabytes per second of logs processed at query time. My name is Marco. I'm a software engineer at Grafana Labs. I'm a Loki contributor and user, and I'm also a Cortex maintainer. I'm mentioning Cortex. Cortex is a distributed storage for metrics. I'm mentioning Cortex even if it's for metrics, while Loki is for logs, because they both share the same architecture, and we have a pretty good amount of code base shared between Cortex and Loki. So even if I spend most of my time working on Cortex, many of the changes we do are actually used by Loki as well. In this talk, I'm going to give you a brief introduction about Loki, a quick demo, and then the second part of the presentation will be a deep dive into the Loki architecture and storage. Now, the typical problem we have is a distributed system composed by many applications or microservices, each one logging tons of log, and we want a cost-effective way to collect those log, store them, and then eventually query them back. The way Loki works is based on an agent called Promtail, which you install on each node running your applications or services. And what Promtail does is tailing the logs from the local file system and pushing those logs to a central server, which is Loki. And then you query back your logs using Grafana, or we also provide a command line tool called LogCLI. Now, to better understand Loki, we have to do a step back, and we need to understand the log anatomy in Loki. So given a single log entry in Loki, each log entry is composed by 3 components: a timestamp, a set of labels, and the log line, like the message you log from your own application. Now, the labels are key value pairs. If you are familiar with Prometheus, they have the same exact syntax of Prometheus, and they are metadata you can attach to each of your logs. Like the application which is logging, or the node information about where the application is running, and so on. And this metadata is configured through Promtail, the agent which pushes the logs to Loki. Now, an important trade-off picked by Loki is that Loki does not index the content of the log. I mean, the message you log from your own application or the entire content of the access log is not indexed by Loki. What we index actually is the timestamp and the set of labels. So what happens at query time is, given a time range and your query, what we do is to filter down all the logs by timestamp, by time range, and the label matchers, and we use an index for this. And then, given the resulting logs, we do further scan the entire content in order to filter them down by the content. A group of logs with the same exact labels is a log stream. And a second trade-off picked by Loki is that given a single log stream, so a series of logs with the same exact labels, Loki requires that the client, like Promtail, the agent, push those logs already sorted by timestamp. This means that if Loki receive out of order logs given a specific log stream, Loki reject those logs. This is not just a detail. This is actually a design decision we picked when we built Loki. Because in this way, we don't have to do any resorting, neither at ingestion time, when we receive the log, neither at query time. Because for each log stream, each log stream is already sorted by timestamp. Now, don't get too much scared about this, let's say, constraint, because Promtail, the agent, can be configured to actually fudge out of order timestamp. So if for any reason your application logs with a timestamp which is out of order, Promtail can be optionally configured to fudge the timestamp which are out of order in order to not get any log rejected on the server side. And then you query your logs. Now, the query syntax is pretty similar to, at least the first part of the query syntax is pretty similar to Prometheus, because the query syntax is composed by a log selector and a filter expression. Now, the log selector is used to filter the logs by the labels. So given all the log streams we do receive on the server side, when you query back your logs, you can filter them by labels. And we use an index to filter the logs by labels. In this case, we are filtering by application equal nginx, or the instance, in this case IP, regex start with 1. And then, given the resulting logs, you can further filtering down the logs by the content, like the content of your log line, with the filter expression. And this second step, filtering, is done doing a full scan of the logs. So there's no index. Which in other terms means we have basically built a distributed graph, if you think about it. Now, Promtail, the agent which again is used to ship the local logs to Loki, does 3 things. The first one is discover local logs. And then, for each log, like a log file, you can configure a pipeline to process those logs. You can attach label, you can transform the logs, you can drop logs you don't want to push to Loki, and so on. And then, at the end of this pipeline processing, we do push the logs to Loki. Promtail is not the only way available to push logs to Loki. We have plugins for FluentVit, FluentD. We also provide a Docker driver. We have an integration with syslog-d. But Promtail, let's say it's the native way, and it's the way I'm going to show you in the next demo. Now, one of the most interesting things to me about Promtail is that Promtail supports Prometheus-style service discovery, which means we specifically support the static service discovery and the Kubernetes service discovery. Now, the static service discovery is common to most of the logging solutions. You can configure Promtail to scrape the logs from the local file system, configuring the file path of the logs. But if you run your applications on Kubernetes, you can actually use the Kubernetes service discovery. And the Kubernetes service discovery, what does is Promtail keeps a connection open with the Kubernetes API. And we continuously discover all the pods running on the node where Promtail is running. And in this way, we can do 2 things. The first one, we can automatically discover the pods and we can scrape all the logs for each container running on each pod on that node. And the second thing is you can configure Promtail to dynamically inject labels to each of your logs based on the Kubernetes metadata, like the pod labels or the node information. In this case, we are attaching the name of the application, which, I don't know, could be a pod label. We can attach the node IP, the node name, and so on. basically any information, any metadata, which Prometheus Kubernetes service discovery support is also supported by Loki, because in practice, under the hood, we use the same service discovery from Prometheus. There are 3 ways to run Loki. The first one and the easiest one is the so-called single binary mode. So Loki is just one binary, pretty much like Prometheus. You can download it, you can run it on your computer, you can also run it with some little limitations on multiple nodes, so in a little cluster. And it's usually used for small installations, and it's the way I'm going to run Loki in the demo. The second way is the microservices way. So when you run Loki in the single binary, what we actually do is running multiple services within a single process. But what you can actually do is to pick each of those services and deploy them separately in order to be able to horizontally scale each of the services which compose Loki. We're going to see the microservices architecture in the second half of the presentation. This is used usually for large installations. It's the way, for example, we run Loki at Grafana Labs. The third way is to use Loki as a service. Grafana has a cloud offer called Hosted Logs, which means we do run Loki for you, and you configure Promtail on your nodes. You push the logs to Loki managed by Grafana, and you get back an endpoint, an HTTP endpoint, which you can use in Grafana, the dashboarding tool, to query back your logs. So as I mentioned previously, I would like to give you a quick demo. I'm going to use the single binary, which means I'm going to run Loki on my laptop. I'm going to run Promtail on my laptop as well. And for this presentation, I downloaded the latest version from the GitHub release page, which is the 130. And I have 2 binaries on my computer, Loki, the server, and Promtail, the agent. I built a simple script to generate fake logs, just to use for this presentation. It logs 10 logs per second. And the format is pretty similar to the Golog format. So it's timestamp equal a timestamp, level equal the log level, info or error, the application name, and the message, which is the message that the application is logging. Then I configured Loki, the server, to run with the local file system as a storage, so that everything runs on my laptop. And I've also configured Promtail to tail my log file where the bash script is logging the fake logs. For each of those logs, it's attaching a static label called type equal demo, which I'm going to use later to easily query back the data. And I'm going to parse using a regex the log line. So I'm picking the timestamp, the level, the application, and the message. And I'm setting the log timestamp based on the content of the log line. Otherwise, by default, is the time when Promtail scraped the logs. I'm setting a couple of labels, the name of the application and the log level, which are inside my log line. And I replace the log line, removing the timestamp, the level, then the application, and just keeping the content of the message. So I already have this bash script generating some logs. I'm going to run Loki, and I'm going to run Promtail. So at this point, we have Promtail, which tail this log file and push the logs to Loki. I also have a local installation of Grafana. So I'm going to add a new data source to Grafana to query back this data. So I select the Loki data source, and I configure the endpoint of my local Loki. It's running a Docker container. I save. It's green. So I don't know if you are familiar with Grafana. Grafana has a panel called Explore. Is it large enough? Maybe this is better. the Explorer can be used to manually write queries, whether they are metrics or logs. And it's, to me at least, it's a convenient way to experiment with your data before building dashboards. What we care for this demo is the time range. So let's pick even the last 5 minutes of data. And we write the first query. So the queries are written in a sort of Prometheus-style query language. So basically, we select the labels of the logs we want to query. As I mentioned before, for all the logs, I'm adding a label set called, a label pair called name type equal demo. So if I run this query, what I get is the list of the entire logs which my fake application, which is the bash script, is generating. So on the top, we see an histogram with the logs splitted by log level. In this case, the bash script is just generating logs with the info and error level. And below, we see the entire list of logs. We can zoom into each single log line, and we can see the label set for that specific log line. So we can see that the application which was logging this specific log was the API application, the file name, and the log level, and so on. Now, let's try to query data. Let's say that we just care about errors. There's some issue in production. We want to check out what's happening. So we can further filter down our logs by the log level. OK, so now we just got the error logs. We can now start to filter further down the logs based on the content. So if we look at the logs, we can see there's the logs, the fake logs are view user, logout user, login user. They try to simulate like activities or update user. Let's say we just care about the authentications. So we can look for the logins. And now we have further filtered down our logs, just showing them the one that contains the login. Or we can use a regular expression, and we can just look for login or logout. Here we are, and we have a list. You can pipe this filtering with hand conditions. So for example, if we pipe user 82, we are going to see the login and logout for the user 82. Now, the second interesting thing of Loki is that it allows you to extract metrics from logs. So far we have filtered our logs and we are viewing our logs. But what you can actually do, switching the button on the top between logs and metrics, we can switch to the metrics. Now, if you switch to the metrics, I'm going to simplify the query. We can compute metrics using aggregation functions, using actually the same aggregation functions of Prometheus. So if you are familiar with Prometheus, what we can do, for example, is to calculate the rate of logs per second calculated over a 1 minute time window. So we can apply the rate function with a 1 minute time window to our LogQL expression. And what we see right now is, maybe like this, is for each log stream, and again, a log stream is a unique set of labels, we can see the rate of logs per second calculated as a 1 minute time window. So each data point is 1 minute time window, the rate per second. And then it's a sliding window going back. And this is each single pixel we see there. Now let's say we care the rate per second not for each log stream, which in our case is the API application logging error level, the API application logging info level, and then we have backend application logging error. backend application logging info. Let's say we just care about the split between the log levels. We can further aggregate the rate using a sum. So we can sum by level of the rate. And what we get now is the rate per second of logs splitted by the log level. In the same way, we can build dashboards. So I'm going to build a new dashboard. I add a new panel. And in this panel, we are going to copy and paste our query. Last 15 minutes. OK. And this is, again, the same query before, but moved into a dashboard. And we can add a second panel. But now we add the logs panel. The logs panel shows you the content of the logs. So this is not a metrics query. This is a log query. And let's say, for example, we are just interested into the errors. So we filter by error. And what we see here are metrics extracted from logs and the logs. And when you change the time window, like you select a portion of your chart and the time window, the time range get reduced, the logs update accordingly so that they are kept in sync. Good? Great. Do you want to ask a question now, or do you want prefer to wait? As you wish.
My question is about Promtail. How it behaves if the log file is rotated underneath.
OK, it follows the rotation.
Follows?
Sorry?
Follows?
Follows. Yeah.
And how did and how get informed about the new file descriptor?
Oh, OK. We register events on the file system.
Okay.
So it's done on file system mode, which means that it's platform dependent.
Yeah, but we do support multiple platforms.
One question, how that?
I have another half of the presentation. What do you think if we move all the questions to the end? Is it, because maybe some questions like this one may be answered in the second half. Okay. And then I will be available the entire night if you want. Now, I'm trying, I can pick my microphone. I'm trying to give you a better understanding of how Loki works. So far, Loki has been a black box, right? I just told you, OK, there's this Loki server, but I didn't tell you how it works, how the storage works, and so on. So now I'm going to try to give you a sort of deep dive. I will make it as much simple as possible, or at least I will try. So when Promtail pushed the logs to Loki, the entry point when you run Loki in the microservices mode, so when you run a cluster for Loki, is the distributor. The distributor is a service which does three things. It validates the input logs, it shard and replicate the logs across a pool of ingesters. The ingester is another Loki component which keeps all the received log streams in memory and builds chunks of compressed logs. So for each log stream, it builds a chunk. A chunk is like a compressed buffer, okay, of log received. And once a chunk is complete, which means it's full, the ingester flushes the chunk to a shared storage and offload the chunk from the memory. Otherwise, it will go out of memory soon. On the read path, when you run a query using LogCLI or Grafana like we did before, the entry point is the querier. The querier is the third service of Loki. And what it does is, given the input time range of the query and the query expression, it fetches the chunks for the log streams matching the label selector in the query, both from the ingester and the shared storage. Now, the ingester contains the latest received logs, which have not been flushed to the storage yet. while the storage contains all the historical logs, right? Which have already been flushed by the ingester. And then the querier received those chunks of data, which is still compressed. The querier decompresses the chunks containing the logs and does a scan, a full scan of those logs in order to filter down the logs by the log line, which is not indexed. So each log stream, like this one or this one, over the time builds up a series of chunks. And each chunk contains the compressed logs for a specific time range. Like between the time 1 and time 2, we have one chunk for each log stream. And then between the time T2 and T3, we have another chunk for each log stream, and so on. And if we look inside each chunk contains all the compressed logs for one single log stream given a specific time range. So, since one Loki requirement is that all the logs must be pushed to Loki already sorted, we don't need to index every single timestamp inside the chunk. We just need to index the minimum and maximum timestamp of the chunk, because if you have the minimum timestamp, the maximum timestamp, and all the data inside is sorted, we can do a binary search inside in order to find the logs given a specific time range. So, the chunks, as I mentioned previously, are filled up in the ingester memory, and they are flushed to the storage once they are complete. And the chunk is considered complete when the maximum chunk size in megabyte is reached, or an idle time is reached. Think about an application which is, which you decommission, so it's stop logging. That log stream or the log stream generated by that application will not push logs anymore. At some point, the logs which are in memory in the ingester needs to be flushed to the storage. Reason why we need an idle time. We support several backends for the chunk storage, which again are the compressed logs. If you run on AWS, we support S3 or DynamoDB. Actually, S3 is also an option picked by people which is not running on AWS, but use a storage which is S3 compatible. If you run on Google, we support GCS and Bigtable. If you run on-premise or other clouds, we support Cassandra. Or if you run Loki on a single node, like I did in the demo before on my MacBook, we support also the file system, the local file system. Now, each single chunk is indexed using an inverted index. So each chunk is indexed by the label set, the minimum timestamp of the logs inside the chunk, and the maximum timestamp. This index is used at query time by the queriers in order to narrow down the chunks it needs given a specific time range, input time range, and query. And we support a few storages as well for the index. AWS DynamoDB, Google Bigtable, Cassandra, again, if you run on-premise or other clouds, or if you run on one single node, like the demo I gave you before, we support BoltDB, which is integrated into Loki. Now, if we get back to the original architecture, I hope now the shared storage is no more a black box. Now we know that actually it's composed by two storages. The chunk storage, which contains your compressed logs, and the index storage, which contain an inverted index, which index each chunk by the label set and the time range of each chunk. Now, previously I mentioned that when Promtail pushed the logs to Loki, the entry point is the distributor. And I also mentioned that one of the things the distributor does is sharding. Since the ingesters need to keep all the logs in memory for a short time until we build up the chunk, which is then flushed to the storage, if you have a high volume of logs, you will probably need to horizontally scale those logs. Those ingesters. So the distributor, given each single log received in input, compute an hash of the label set, and given this hash, picks one of the ingesters from the pool of available ingesters to which the specific log should be pushed. I know your next question, maybe. What happens if an ingester dies? So since the latest logs are kept in memory, if an ingester dies, the logs are lost. The replication is the solution to, let's say, protect from this failure scenario. So Loki allows you to configure a replication factor, which we suggest to be 3, which means for each single log stream we do receive in input in the distributor, we compute the hash, and given that hash, we write that log to 1, 2, and 3 ingesters. So if an ingester dies, the log that have been pushed to ingester 1 have also been pushed to other 2 ingesters. In this case, in the example, the number 2 and the number 3. So try to stay with me. I want to talk about this one because my boss is a super fan of this one, and I became a super fan as well because it's a very flexible data structure we use for many things, including how the replication and sharding is built. So the replication and sharding is based on the ring. The ring is just a data structure, okay? Like any data structure. And it's distributed in the sense that this data structure is shared across the pool of ingesters and distributor, which means every time this data structure changes, all the nodes within the cluster will get the updated data structure. Now, the hash I was talking before in Loki is a 32-bit hash. But to keep this presentation simple, we are going to use an hash space with the keys between 1 and 10. So let's say that we have our hash space, which is the number which our hash can assume. 32-bit in Loki, between 1 and 10 in this demo, in this presentation. When an ingester is started, it generates a random value. And the random value is the value, the key, that the ingester picks within a ring. A ring is just our space containing all the keys. So the ingester number 1 start, it generates a random value number 2. And then the ingester number 2 start, it generates a number value 6. And then the ingester number 3 start and generate a random value 9. When the distributor compute an hash of our input label set, the hash value is within our key space, 32-bit in Loki, 110 in this presentation. And what we do is the distributor check if there's any ingester with the same value of the hash. If there's no ingester with the hash, which we computed the labels, what the distributor does is walking through the ring in order to find, clockwise, in order to find the first ingester, the first healthy ingester within the ring. And in this case, the log is pushed to the ingester number 2. If you enable the replication, we don't stop at the first ingester we find. What we do is continue walking within the ring until we find 2 more ingesters if you have a replication factor of 3. So in this case, it will continue to walk, you find the ingester number 2, and then the 3, and then the 1. And that's how the replication and sharding is built, and that's actually how several other features are built, several other features which require some sort of coordination are built within Loki. This data structure needs to be shared across the nodes of your Loki cluster. So, we need another backend. We support console, etcd, and we recently introduced gossip support, which means we can build a peer-to-peer network between all the Loki nodes, so that you don't need to have console or etcd just to keep the ring data structure, which is a few kilobytes of data. Now, the good news is that we don't need a strong persistence. To give an example, we run Loki in production and we just run one console instance in memory, so even without storing the data to disk, without any HA or stuff like this. Why? Because even if you lose console or etcd for a short time, and even if all the data inside is erased, when a new instance, which is of console or etcd, start up, even if they're empty, all the nodes within Loki are able to reconstruct the ring, the data structure stored within console or etcd. The only downside is that if any change to the data structure will happen during the console or etcd downtime, the change will not be propagated to the other nodes. The change will be propagated as soon as the backend is restarted. There would be much more I would like to talk about, but obviously I don't want to give you further overload of information. We support caching in order to reduce the operations against the shared storage, both on the write path and the read path. Loki support multi-tenancy, which means you can enable the multi-tenancy in order to have logs fully isolated between users. This is the way we run our own Loki as a service solution, hosted logs. This is also the way single companies use when they have teams and they want the team A to just be able to query the logs of the team A and not exposing the logs of the applications of one single team to the entire company. But before leaving, there's one last thing I actually would like to talk about, which is a new service we introduced, or fairly new service we introduced, which is an optional service you can put in front of the queryers and is used to speed up the query performances. And it's the query frontend. Now, the query frontend does two things. The first one is affair scheduling. Now, let me explain you the problem without the query frontend. So let's say we don't have the query frontend, but you run Loki at scale, you have multiple query instances, and you have a load balancer in front of the query instances, so without the query frontend. What happens is the load balancer receives a query, and it does a round robin across the queries in the backend. So it receives one query, it goes to the query number 1, second query, query number 2, and so on, and it does a round robin. The problem is not every query put the same load on the system. There are queries which can be executed in 100 milliseconds, which are queries which can scan a bunch of logs and may take 30 seconds to execute. The problem is that if you have a pretty high traffic, at some point you may end up into a situation where the load balancer send the query to a query which is already overloaded, but you have another query which is idle. The query frontend introduces a queue, an in-memory queue. So when we send the query, the load balancer balances across multiple query frontends for high availability purpose, and the query frontend put the query received in input into an internal queue, and then the querier, when it's idle, picks another query from the queue. In this way, we can better distribute the workload across the queries. The second thing, which is built on top of the queue, is the parallelization. So let's say that you run a query, like the one I used at the very beginning of the presentation in the example, and you run this query for a large time range. Like I want to see all the Nginx errors for the last 24 hours. Now, if you have a pool of queries, without the query frontend, the query will be executed by one single query. So the other queries are unused. What the query frontend does is picking this query with a large time range and splitting the 24 hours time range query into 24 one-hour queries. So we put in the internal queue 24 queries, each one for one single 1 hour time range, and then the pool of queries will pick those queries to execute from the queue, will send back the result to the query frontend. The query frontend merge the results, and returns back to the client, like Grafana or LogCLI, the logs sorted by timestamp. That's pretty much all. I've been very happy to be here.